Well, first of all, I would like to thank the organizers for inviting me to give this mini course. It's great to be part of this thematic program in infinite dimensional geometry. I work in operator theory and infinite dimensional geometry, more precisely in the Banach setting. The general framework of this mini course will be operator ideals, operators ideals in Hilbert spaces, and Banach-Lie groups and their homogeneous spaces associated to operator ideals. The specific topics of this mini course will be in the first lecture. It is about restricted diagonalization. This is a diagonalization problem, but instead of using the usual unitary operators to diagonalize, we will use the smaller group associated to operator ideals, and we'll ask about the diagonalization with that group. In the second lecture, we will study the Moore-Penrose inverse in certain infinite dimensional homogeneous spaces associated to operator ideals. And in the last lecture, we will study the polar decomposition. The polar decomposition is the factorization of an operator in a partial axiometric part and in the operator modulus. So we will treat these two factors as maps, again, in certain homogeneous spaces associated to operator ideals. I have to say that this mini course is organized to present more or less recent work, joint work with Pedro Macei. Well, the first lecture about restricted diagonalization, I begin with some definitions and elementary properties about operator ideals. We work in H, a separable infinite dimensional complex Hilbert space. B of H will be the algebra of bounded operators acting on H. The definition of an operator ideal is as follows. An operator ideal is a two-sided ideal of the algebra B of H. The ideal is said to be proper if it's not trivial and it is not the full algebra. Well-known examples are the following. For instance, the finite rank operators, the compact operators, and here a remark that goes back to Calkin is that every proper operator ideal must be contained in the compact operators and must contain the finite rank operators. Another well-known example is the Piaget ideals. The Piaget ideals are those compact operators such that the trace of the modulus to the pth is finite. Then one can also take the pth road, and when p is greater or equal than 1, this gives a complete norm, so these are Banach spaces. But for p between 0 and 1, this quantity here does not satisfy the triangle inequality. One have to take the pth power of this, and then the induced metric is complete. So for p between 0 and 1, these are p Banach spaces. Another example is the operators are the operators ideals associated to symmetric norming functions. A symmetric norming function is a norm defined in C00. This is the usual space of sequences where all the terms are 0 except finitely many of them. So symmetric norming functions satisfies these two conditions. a condition about permutations and this normalization condition. So if we take an operator, a compact operator, we will denote by Sn of t, the sequence of singular values arranged in non-increasing order. So this set S sub phi, given us by this condition, the supremum on the singular values, turns out to be also an operator ideal. Special cases are the P-Schatten ideals with P greater or equal than 1. The symmetric norming function there is the LP norm. So we have this another way to express the P norm of Schatten ideals using the singular values of the operators. There are, of course, more involved examples of operator ideals, but I will stop here with the samples. Now we will define the unitary group which is associated to the operator ideal. We denote by U of H, the usual unitary group. So given an operator ideal, J, one can associate a subgroup of the unitary group as follows. Uj are those unitaries such that U minus the identity belongs to the ideal. We will call them restricted unitary groups associated to the ideal J. Some properties of these groups: if J is a proper operator ideal, then Uj is not the identity and is not the full unitary group. For each unitary operator in Uj, we observe that the spectrum is a sequence of modulus 1 that can only accumulate at 1. This is because, as we say before, this difference belongs to the operator ideal, and all operator ideals are contained in the compact operators. So the spectrum is as follows. About the geometric structure of these groups, we have this result. When J has a complete norm such that it is greater than the operator norm, then Uj is a real Banach-Lie group in the topology induced by that norm, and its Lie algebra is given by the anti-Hermitian operators in the operator ideal. Now I will say the precise definition of restrict diagonalization, and I will review some results about restricted diagonalization. We first recall the definition of usual diagonalization. We say that an operator A, a bounded operator, is diagonalizable if there exists an unitary such that UA star is diagonal with respect to some orthonormal basis of H. The definition of restricted diagonalization was introduced in a work by Beltita, Pagnay, and Weiss. Suppose that we fix J an operator ideal and E an orthonormal basis. We say that an operator A is Uj diagonalizable with respect to the basis E if there exists a unitary in this restricted group associated to the ideal J such that UA star is diagonal with respect to the basis E. We have to point out here a difference between the usual diagonalization and restricted diagonalization. Note that here we say that the conjugation of A by some unitary is diagonal with respect with some orthonormal basis. In this case, one can pass from a basis to another with a unitary. But in this case of restricted diagonalization, one has to fix the basis because one cannot always pass from a basis to another using this kind of restricted unitaries. Well, a little of notation. We will put D for the diagonal algebra with respect to a fixed basis E, and the set dj of H will be the set of all diagonalizable uj diagonalizable operators with respect to that basis. Some results about restricted diagonalization. Well, the first I would like to mention is the work by Daniel, Patnaik, and Weiss. They studied conjugacy classes of Cartan subalgebras in operator ideals. So in that work, they introduced the notion of restricted diagonalization. They also offer more general versions of restricted diagonalization. Instead of take this set, dj b of H, they also have another more general notions where you can change this b of H to another operator ideal, I. So this means that the diagonals are in some other operator ideal, I. And here below are some results about restricted diagonalization in that work. For an operator ideal, we will put the square of the operator ideal to this span, which is again an operator ideal, and it is obviously contained in the ideal J. So they have this necessary condition for an operator A such that is uj diagonalizable. Suppose that D is the diagonal, then this difference must be in the square of the ideal. Another result here is that given two orthonormal bases, E and F, and if we have that these differences in the norm of the Hilbert space are uniformly bounded from below for all n, m, and gamma of modulus 1, then an operator which is diagonal with respect to some orthonormal basis E cannot be UK, K are the compact operators, cannot be UK diagonalizable with respect to the other basis F. They use this last proposition to show that for a proper operator ideal, there are uncountable many conjugacy classes of Cartan subalgebras. Another result about restricted diagonalization is the following. This is a sufficient condition, but only for the Hilbert-Schmidt operators. This appeared in a work by Hinkanen in the 80s. The idea is to look at the operator entries with respect to a fixed orthonormal basis E. So if these very involved sets of inequalities hold, then one can get that the operator A is uj diagonalizable, where J are the Hilbert-Schmidt operators. Another notion that is related to restricted diagonalization is the uj unitary equivalence of orthogonal projections. This means that we have two projections, P and Q, and we want to conjugate P on Q, but with a unitary in the restricted unitary group. So for this problem, it is useful to introduce the idea of the index of a pair of projections. Suppose that given PQ two orthogonal projections such that this operator QP view as an operator from the range of P to the range of Q is a Fredholm operator, then we say that the pair PQ is a Fredholm pair and the index of the pair is defined as the index of that Fredholm operator, which can also be computed as this difference of dimensions. Here is the dimension of the null space of Q intersected with the range of P, and here the dimension of the range of Q intersected with the null space of P. To the best of my knowledge, this was first introduced in a work by Brown, Douglas, and Fillmore. Under a different name, they call it essential codimension. And then there is a well-known work by Ebron, Seiler, and Simon, where they use the index of the pair of projections to give some formulas about the trace of the certain pth powers of differences of projections. In the same year, it appeared a work by Unrein and Sina. They studied the index of pair of projections from a different viewpoint. They use what is known as the Helmholtz two projection theorem to understand the index of projections. And more recently, I would like to mention a result by Esteban Andruchov. He showed that two projections in the Grassmann manifold of a Hilbert space can be shown by a geodesic, indeed by a minimal geodesic, if and only if the index of the pair of projection is 0. Indeed, the result is more general. One can also apply that result when these dimensions are infinite. Some elementary properties of the index of a pair projection are these. Suppose that we have two Fredholm pairs such that the projections P are orthogonal as follows, and the same for Q. If this condition holds, then P1 plus P2 is again an orthogonal projection, the same for Q. And it turns out to be also a Fredholm pair, and the index can be computed as follows. Another result is that when P, Q are orthogonal projections such that their difference belongs to the compact operators, then we have that PQ is a Fredholm pair. So using the notion of index of the pair of projections, we have this result about UJ unitary equivalence of projections. This is a result by Kaftal and Loraux. This is the more general version of the result about this type of equivalence. Suppose that PQ are two orthogonal projections and we fix J and a proper operator ideal. Then the difference, suppose that the difference between PQ belongs to the ideal and this index is 0, which is well defined because our previous remark. Then this is equivalent to the fact that the two projections are UJ unitarily equivalent. In fact, some previous results for special cases of operator ideals are here. Brown, Douglas, and Fillmore for the compact operators, Stratila and Voiculescu for the Hilbert-Schmidt operators, and Carey for the class of operators induced by symmetric number functions. Now we turn to the problem of UJ diagonalization of normal operators with finite spectrum. We first will try to understand the case of P an orthogonal projection. This is resolved by Loraux, who was a PhD student of Weiss. He proved the following. Given P an orthogonal projection, then P is UJ diagonalizable with respect to some basis E, if and only if there exists a diagonal projection E such that this difference belongs to the operator ideal. The forward implication, we will see that implication later for the case of a normal operator with finite spectrum. It's just a simple computation. But about the backward implication here, the idea is that when one has that the difference of P between a diagonal projection belongs to the ideal, then the index of the pair is well defined. But that index may not be zero. So the idea is to modify the diagonal projection. The diagonal projection, of course, in a basis, is a diagonal operator with zeros and ones. So you can put zeros or ones in order to have that P and another diagonal projection have index 0, and then you can use the result about UJ unitary equivalence of projections. In the general case, we have a normal operator with finite spectrum. Pi will be the spectral projections, and lambda I the eigenvalues. So we have this spectral decomposition of A, and Loraux proved the following. A normal operator with finite spectrum is UJ diagonalizable with respect to some basis E. Here the operator ideal J is also, of course, fixed. This is equivalent to the existence of a family of diagonal projections such that their differences belong to the operator ideal for all I. I would like to give an idea of the proof. Well, the forward implication, we have that there exists a unitary in the restricted group such that this conjugation belongs to the diagonal algebra. So we can put EI as follows: U, Pi, U star, where Pi are the spectral projections of the operator. Then, by the Borel functional calculus, these are indeed diagonal projections. And then we can compute this difference, which can easily view that belongs to the ideal, because here we have U minus the identity and U star minus the identity. For the converse, we have that there are diagonal projections such that these differences belong to the ideal for all I. So the idea here is to change again the diagonal projections. Diagonal projections commute, so the product of diagonal projections is again a projection, so one can use that to produce another family EI prime of diagonal projections such that their differences belong to the ideal. Now, this index is 0 for all I, and also the new diagonal projections are mutually orthogonal. Then this reduction allows to construct a unitary in the restricted group such that conjugate all the spectral projections on these new diagonal projections using induction and the mentioned properties of the index. This later condition here with the spectral projections exactly means that then the operator UA U star is diagonal. Now we turn to restricted diagonalization, but in the case of infinite spectrum. I would like to tell you what we did with Pedro Macei here in this case. So we study an operator A with infinite spectrum that is a normal diagonalizable operator with infinite spectrum. We have that the operator now has this spectral decomposition with infinitely many spectral projections. This series converges in the strong operator topology, and in this case, it can be shown that the point spectrum is dense in the spectrum of the operator. So the first attempt to study this case is to try to mimic the idea of Loraux, but now with infinitely many projections. That is this hypothesis, the existence of a family, an infinite family of diagonal projections, but it can be shown that this is not sufficient for UJ diagonalization. So our idea to find a sufficient condition is first to give a new condition that is equivalent to the previous two conditions of Loraux in the case of finite spectrum. We take a normal operator with finite spectrum. Here, the first two conditions are Loraux conditions, and we add a new condition, which is about these two sums involving these products of projections. EI is again a diagonal family of projections. And we require that these sums belong to the operator ideal. So this is another equivalent condition to the other conditions. And this motivates how to deal with the infinite spectrum case. You see here, the idea will be to take the limit here in N and also here, and still require that the limit belong to the operator ideal. That idea, that innocent idea, it's great that really works, but some questions that one may have is in which topology we take that limit, and of course, I say that this will be a sufficient condition, but is that also a necessary condition? So this is our main result about restricted diagonalization with infinite spectrum. We take A diagonalizable operator with infinite spectrum. Assume that there is a family of diagonal projections such that these two series have limit in the operator ideal. And the topology we are using here is the weak operator topology, that is the topology defined in terms of inner products and the vectors of the Hilbert space. So if this is condition about the series whole, then A is UJ diagonalizable. And for the converse, we have to add another hypothesis, which is this. The converse holds for the class of arithmetic mean close operator ideals. If A is UJ diagonalizable and J is an arithmetic mean close operator ideal, then there exists a family of diagonal projections such that the above conditions with the series hold. Here below is the definition of an arithmetic mean close operator ideal. Suppose that T is a compact operator, and for some K in the operator ideal, the following family of inequalities between singular values hold, then we have that T must belong to the operator ideal. So in the case of arithmetic mean close operator ideal, our result is a characterization of UJ restricted diagonalization. Some examples of arithmetic mean close operator ideals are the P-Schatten ideals with P greater or equal than 1. Also, all the ideas defined in terms of symmetric norming functions. Examples of operator ideals that are not arithmetic mean close are the final Reich operator ideals, the P-Schatten ideals, where P is now between 0 and 1. And also I have to say that the notion of arithmetic mean close operator ideals is a relevant notion in the theory of operator ideals. This is because of a work by Dijkema, Fischl, Weiss, and Gozicki, where they give a characterization of commutator spaces of operator ideals in terms of arithmetic means of the singular values. So I would like to give an idea of the proof again here, but first some remarks. If J is not arithmetic mean close, then we have an example that the converse does not hold. The example is with J, the finite Reich operators. The conditions given in the series, in the two series, imply Loraux conditions, that is, these differences belong to the operator ideal. And also, once the two series converge in the weak operator topology, then it can be shown that they also converge in the operator norm because of some properties of compact operators. But of course, it is better to state the result, our theorem, using the weak operator topology, which is an easier topology to prove convergence. So for the proof, we start with the backward implication. Again, as in the finite spectrum case, we can define the diagonal projections by using Borel functional calculus, using the spectral projections. Then if we take one of the series, the other series, the argument is analogous. So we take this series, we compute, and please go here to the last line. We have two terms. These terms obviously belong to the operator ideal. What we would like to prove here is that this series converge to some operator in the ideal. So the first term, it is obviously in the ideal, but in the second term, there is a part here, a factor here in blue, that it is not trivial that this part belongs to the ideal. So let me explain a bit that. In fact, in the last part here, it is where we have used the fact that the ideal J is arithmetic mean close. So to explain that, in general, when we have a family of mutually orthogonal projections, we can define the pinching operator, which is the operator that gives to an operator T another operator that here is like a block diagonal decomposition of the operator T in terms of the given family of projections, EI. So it can be shown that pinching operators satisfy these families of inequalities, which is the same family of inequalities that appear in the definition of arithmetic mean close operator ideals. So using this fact and also that J is arithmetic mean close, we get that this pinching operator of U star minus the identity belongs to the operator ideal. To prove the forward implication, we first note that the condition with the series imply the following. There is an integer, say A1, after which the family of diagonal projections must be mutually orthogonal, and these two inequalities with these pinching operators must hold. Then this is used to construct the following projections. E is a projection defined as follows. This is a limit in the strong operator topology. Since the family is mutually orthogonal after the integer A1, this projection, this E is again a projection. So the same is, one can do the same with the spectral projections and also define here as this sum of products of projections. There are some relations between E, S, and P, but what is important here is that the operator S from the range of P and the range of E turns out to be invertible, and that is S minus P belong to the operator ideal. This fact, the fact that S is invertible, is a consequence of the above inequalities in the operator norm, and the fact that S minus P belong to the operator ideal is a direct consequence of the two series condition. Then we can extend first S to the whole space as 0 in the orthogonal complements and define V as the following partial isometry. Here the dagger means the generalized or Moore-Penrose inverse. This partial isometry has initial space V and final space E and conjugate all the spectral projections, on the diagonal projections, and also V minus P belong to the operator ideal. I will explain this later in a remark. And the next step is using two facts that again will be explained later. Here, these two facts in blue, that the index between the initial and final projection of V is 0 and their difference belong to the operator ideal. One can use the ideas in the case of finitely many projections and consider these finite families of projections. Then using Loraux results, one gets a restricted unitary conjugating all the first spectral projections on the first diagonal projections. And then the unitary U is defined as V in the range of P and as this U0 in the range of the identity minus P. This will be the unitary that conjugates all the spectral projection in all the diagonal projection, and that means that A is UJ diagonalizable. So I will try to explain a bit these parts in blue. The first remark is about the partial isometry V. Behind this, it's a quite simple idea that appears when one studies geometric aspects of projections. Indeed, what we have done in the previous slide with infinitely many projections is a generalization of a well-known result about two projections. When we have two projections such that their distance is strictly lower than 1, then this operator S, constructed as this product of projections, satisfies these properties, and then the unitary in the polar decomposition of S is a unitary which conjugates P on Q. And the second remark is to understand why E and P must have 0 index and E minus P belong to the operator ideal. We prove the following result. It can be interpreted as a characterization of restricted orbits of partial isometries with the following action. Here V is a partial isometry and U is a restricted unitary. So here we are changing with those unitaries, we are changing the range of the partial isometry. So we prove the following result. Given two partial isometries, there exists a unitary such that UV1 is V2 if and only if the difference between these partial isometries belong to the operator ideal and the null spaces coincide. Then using this result, note that here if we multiply UV1 by V1 star U star, we find that the final projections of V1 and V2 are UJ unitarily equivalent. So using the result about that type of unitary equivalence, we get that the final projections have zero index, and also this difference belongs to the operator ideal. So in our theorem, we have used this proposition in the special case where the partial isometry V1 is the partial isometry V in blue in the theorem, and V2 is indeed a projection, which is, of course, a partial isometry. So using this result, we get these facts about the index and the difference of the projections. I have to say that we will return to this result in the second and in the third lecture of this mini course. So to finish, I will give some consequences and related results. A special case is when the operator ideal is such that the square of the operator ideal is arithmetic mean close. Then in this case, we have another condition that instead of the two series condition, we have that A is uj diagonalizable if and only if there is a sequence EI such that now this series belongs to the square of the operator ideal, where the convergent is again in the weak operator topology. For instance, for the class of P-Schatten ideals, one can see that the square of the P-Schatten ideal is the P-half Schatten ideal. So if we take, for instance, P between 1 and 2, then the square will not be arithmetic mean close. But a case where we can use these results is the case of Hilbert's main operators. The square is then the trace class operators. So the operator is diagonalizable with respect to the Hilbert-Schmidt ideal if and only if there exists a sequence of diagonal projections such that this sequence here, this is the Hilbert-Schmidt norm. So this series must converge. Another definition introduced by Meltita, Patnaik, and Weiss is the following. Suppose that we have two orthonormal bases, E and F. Then we say that these bases are J equivalent if there exists a unitary in the restricted group such that maps each element of the basis E on elements of the basis F. So they propose the following interesting problem to understand J equivalence in terms of conditions on the vectors of the basis. So using our previous results, we have this. Suppose that we take J, an auxiliary orthonormal basis, and we define U1 and U2, the following unitaries, mapping this basis J on the basis E and the other mapping the basis G on the basis F, and then put this difference between U1 and U2. Then using the proposition about restricted orbit of partial isometries, in the very specific case where the partial isometries are now unitaries, we have that the two bases are J equivalent if and only if this operator belongs to the ideal. So applied to the case of Hilbert-Smith operators, we have that T belongs to the Hilbert-Smith operators if and only if this series using the vectors converges. This case was, of course, well known before, but the following case about compact operators was not known. In the case of compact operators, T belongs to that ideal. Using this characterization of compact operators with a limit of finite rank projections, one has that the equivalence between the two bases is the same as saying that for all epsilon, there is an integer after which the following inequalities holds for all the sequences in L2. So to finish, some references. There are, of course, a lot of more references, but some of them, here is the work by Dijkema, Fischl, Weiss, Wozicki about the commutator spaces in operator ideals. Two standard references are the book of Gover and Crane and Barry Simon. Some books or notes about geometry where you can find a lot of examples about geometry and operator ideals. The book by Daniel, the book by Pierre de la Harpe, these notes by Neve. Some of the papers we use in this lecture, these ones about the index of the pair of projections, and the paper of Beltita, Banach, and Weiss. Well, our work with Pedro Maisei is this one, the works of Loraux. So thanks for your attention.